Good morning to all of you. Today I am recording the lesson for day 9. Today I am going to take a class on the elastic constants. The topic is simple stresses and strains, and subtopic is elastic constants. So in this class we will study about the elastic constants and their relations, and we are going to have some problems to find out the elastic constants, and then we can have an idea and better understanding about the elastic constants in this chapter. Now for this I have prepared the PPT, and now I am going to share you the PPT, and we'll go for the lesson with the help of the PPT. So our lesson is simple stresses and strains. In that we'll discuss about the elastic constants, and at the end of this lesson we will come to know the relation between the elastic constants, and we can able to solve some problems on the elastic constants. So now we got generally three types of elastic constants. That is the Young's modulus, modulus of rigidity, and Buck modulus. And we got the definition of these three constants, and also we got the Poisson ratio, and we are having some relationship with these constants among the all these elastic constants and the Poisson ratio, and after that we are going to solve some problems. The first one is the Young's modulus. So this Young's modulus is generally applicable during the tensile stress or compressive stress. So whenever a body is subjected to some kind of stress, that may be either tensile stress or compressive stress. Accordingly, when it is subjected to tensile force or compressive force, so it results in the tensile strain or the compressive strain. So Young's modulus can be defined as the ratio of the tensile or compressive stress to the corresponding strain. That means whenever a body is subjected to a force along its lengthwise, that is axial direction. So depending on the nature of the force, either the body may be subjected to tension or compression, and accordingly it may be subjected to a tensile strain or a compressive strain, and also leads to development of the tensile stress or the compressive stress. So whenever it is subjected to a tensile force, the length will increase, the change in length will increase, and it is considered the strain and stress are considered to be positive. And whenever the body is subjected to the compressive force, it will shorten the length. That is the length decreases, and the corresponding stress and strain are negative, and they are taken to be a negative one. Now, therefore, the Young's modulus can be defined as the ratio of the tensile stress or compressive stress to the corresponding strain is called as the Young's modulus, or it is also called as the modulus of elasticity, and it is denoted with the letter capital E, and therefore the Young's modulus capital E is equal to stress by strain. So in this case we will consider the tensile or compressive stress, and the unit is newtons per square millimeter. So whatever the units that we use for the stress, the same holds good for the Young's modulus, because the strain has no units. The next one is the modulus of rigidity. It is also called as the shear modulus. So in this case, the shear forces are taken into consideration. In the previous case, the axial forces are taken into consideration. Now in this case, the shear forces, which will cause the shear stress and shear strain, are taken to be consideration. And whenever a body is subjected to some kind of shear force, so it develops the shear strain and also shear stress. As a result of which the body tend to shear up from original position. So in this case, the ratio of the shear stress to shear strain is called as the shear modulus, or it is also called as the modulus of rigidity. So this is the this modulus also will indicate the rigidity of the material. If the shear modulus is more, then we can say that the material is more rigid as compared to the other, those who are having the less modulus of rigidity. It is also measured in newtons per square millimeter. The next one is the Buck modulus. So the shear modulus or modulus of rigidity can be denoted with the letter G, C or N. The next one is the Buck modulus. So in this case, in the two cases, only one type of the forces are taken into consideration when they are applied only in one direction. But in some cases, the body is subjected to the forces in mutually three perpendicular directions, like the x, y, z along the x, y, and z axis. So in this case, the direct stress means what? If a force acting perpendicular to the area of cross section. So suppose a force is acting along the x direction, then yz will become the width and the thickness. Then yz will cause the area as compared to as when the force acting along the x axis. So the direct force for the yz planes will be the force acting along the x axis. So here, whenever the force acting along the x axis is taken into consideration, then we have to consider the area along the yz axis. So that is called the direct stress. And What is this volumetric strain? We already studied. Whenever a body is subjected to some kind of forces, maybe a single force, maybe three different forces or many forces, then what happens? The volume change occurs. So the length, width, and thickness in case of the rectangular body will change due to the application of the force. So what happens? Initially it has got the volume of L, B and T, and finally the L will change, width will B will change, and thickness T will change. So finally we got the other volume. It may be lesser than that of or more than that of the initial value. But however, the change in volume will occur due to the application of the forces, and so the ratio of the change in volume to the original volume is called as the volumetric strain. That already we have studied and we got the equation for that also. That is denoted with the letter EB. Now, Buck modulus may be defined as the ratio of the direct stress to the volumetric strain. The ratio of the direct stress to the volumetric strain of a body when it is subjected to some kind of forces is called the Buck modulus, and in this case the direct stress can be found as if the force acting along the x-axis, then the area can be taken on y and z axis. Like that the stress can be obtained, and the ratio of the direct stress to the volumetric strain is called as the Buck modulus, and it is also measured in newtons per square millimeters or newtons per square meters, and it is denoted with the letter capital K. Now the next one is the Poisson's ratio. So this also we have already studied. Anyhow, I am just repeating. Whenever a body is subjected to some kind of forces, it is subjected to two kinds of strains. One is called as the linear strain, that is along the axis in which the force is applied, and it is also subject to the lateral strain. So this lateral strain is nothing but the strain of the body perpendicular to the force applied direction is called as the lateral strain. For example, if a body is having the length, width and thickness, and the force is applied along the lengthwise, so the strain produced along the lengthwise is called as the longitudinal strain, or the primary strain, that is equal to change in length by original length, that is equal to delta L by L. Whereas the force also produces some changes in the width and also thickness. So here the width and thickness are perpendicular to the force direction, because force is applied in the length along the lengthwise, and the width and thickness are perpendicular to the length. Therefore, the strain obtained along the width and thickness are called as the lateral strains. And the lateral strain is also nothing but the change of lateral dimension by original dimension. In that way, we can find out the linear strain and also lateral strain. And that lateral strain also called as the secondary strain. And we also got one of the important term, that is the Poisson's ratio. It is denoted with the 1 by m, or mu. So whenever a body, the Poisson's ratio can be defined as like this. Whenever a body is subjected to some kind of forces, the ratio of the lateral strain to the linear strain is called as the Poisson's ratio. It is represented by the letter 1 by m or mu. Here the Poisson's ratio is a ratio of the strains. So that is the lateral strain and longitudinal strains. And so it does not have any units. It is only some value that is constant value. And the Poisson's ratio will remain constant for a particular material, and it is material specific, but it changes from one material to the other material. Next, we are going to have the relation between the elastic constants. So we got the modulus of elasticity E, modulus of elasticity, that is modulus of rigidity C, and Buck modulus K. So first of all, we'll see the relation between the E and C. So we got E is equal to 2C into 1 plus 1 by m. Here E is the modulus of velocity, that is the Young's modulus, and C is the shear modulus, and 1 by m is the Poisson's ratio. The next one is the relation between the Young's modulus E and Buck modulus K. So here we got the relation E is equal to 3K into 1 minus 2 by m. Here 1 by m also equal to the Poisson's ratio. So this is nothing but the E is equal to 3K into 1 minus 2 into 1 by m. So 1 by m is nothing but the Poisson's ratio. Next, coming to the relation between the three constants, that is the three elastic constants, that is the modulus of velocity E, modulus of rigidity C, and Buck modulus K. So we got the relation E is equal to 9kc by 3k plus c. So this is the relation between the three elastic constants. Now we have to use the suitable equation to find out the unknown value according to the problem given. Now we are going to have some example problems on these equations to have the clear idea how to evaluate the all these elastic constants in the different situations. So this is the first problem. So you can write down this problem, then we can have the solution. A bar of 25 millimeter diameter is subjected to a pull of 50 kN. The measured extension over a gauge length of 200 millimeters is 0.1 millimeters, and change in diameter is 0.0035 millimeters. Find the Poisson's ratio and the elastic constants. So here a round bar is given. It is subjected to a pull force, that a tensile force of 50 kN. and in this case the extension is given or the gauge length is given, and also the change in diameter is given. With this data we have to find out the Poisson's ratio and the elastic constants. Now this is the bar as per the given problem and subjected to the force as shown in the figure. So it is a bar, that is a circular bar of 25 mm diameter and 200 mm length. It is subjected to an axial pull, that is a tensile force of 50 kN at both ends. Now this is the given problem, and here due to the application of the force in the problem itself, it is mentioned that the extension observed to be 0.1 millimeters. That means if we take the midpoint, from midpoint at both sides it will have an extension of 0.05 millimeters, and here whenever the length increases due to the axial force, the diameter will reduce, and here the same is given as the reduced diameter is equal to 25 minus 0.0035 millimeters. So the same thing is shown in the figure. Now this is the given data. The diameter of the bar D is equal to 25 millimeters. Load P is equal to 50 kN, that is 50,000 newtons. Length L is equal to 200 millimeters. Extension of the rod delta L is equal to 0.1 millimeters. The change in diameter delta D is equal to 0.0035 millimeters. So this is the data given in the problem. Now coming to the solution. So first of all we have to find out the area of cross section. So we know that area of cross section is equal to 5 by 4 into d square. So substituting the d is equal to 25, the area is 490.625 square millimeters. Then we have to find out the stress value. Stress F is equal to load by area. So here the load given as 50,000 and area is we calculated, we got 490.625. So by substituting the load and area values, the stress F is equal to 101.86 newtons per square millimeter. That is the stress value. Then we have to find out the longitudinal strain. So here the longitudinal strain or the primary strain E is equal to change in length by original length. The change in length is recorded as 0.1 and original length we got 200. So 0.1 by 200, it coming to be 5 into 10 power minus 4. So no units. Next the lateral strain. So here because it is a circular rod, so when the force is applied along the length, the diameter will become the lateral dimension, and lateral strain is nothing but the change in lateral dimension by original lateral dimension. Here the nothing but the change in diameter by original diameter. So that is equal to 0.0035 by 25. It comes to be 1.4 into 10 power minus 4. Now coming to the Poisson's ratio. The Poisson's ratio is equal to lateral strain by longitudinal strain. So that is equal to 1.4 into 10 power minus 4 by 5 into 10 power minus 4. So it is equal to 0.28. So the Poisson's ratio on 1 by m is equal to 0.28. Next one is the Young's modulus. Here we know the stress value and strain. So in this case the strain means we should take the longitudinal strain or the primary strain. So Young's modulus is equal to we got stress is equal to 101.86 and the longitudinal strain is equal to 5 into 10 power minus 4. Then it is coming to be 2.03 into 10 power 5 newtons per square millimeter. Generally the Young's modulus value is very higher value and it is generally given as some value into 10 power 5 newtons per square millimeter. So in this case it is coming to be 2.03 into 10 power 5 newtons per square millimeters. The next one is the modulus of rigidity. C is equal to, so we got the equation, that is we got the equation. What is the equation? E is equal to 2C into 1 plus 1 by m, whereas C becomes in terms of the value of the C in terms of E and 1 by m is nothing but C is equal to E by 2 into 1 plus 1 by m. Here 1 by m is the Poisson's ratio value. So substituting those values, 2.03 into 10 power 5 by 2 into 1 plus 0.28. So ultimately we are getting the modulus of this C is equal to 0.79 into 10 power 5 newtons per square millimeter. The next one is the Buck modulus. So for this also here we got the equation E is equal to 3k into 1 minus 2 by m, and when the k also equal to E by 3 into 1 minus 2 by m. So here nothing but the 3 into 1 minus 2 into 1 by m, because 1 by m is nothing but the Poisson's ratio value. So by substituting those values, it coming to be 1.54 into 10 power 5 newtons per square millimeter. So here we can observe that the Young's modulus is equal to 2.03 into 10 power 5 and modulus of rigidity is equal to 0.79 into 10 power 5, and whereas the Buck modulus is equal to 1.54. So you can say for the same material and it is subjected to some kind of load, always the Young's modulus is having the more value as compared to the Buck modulus and the shear modulus. This we can note from this problem. Next, the other problem. We'll go to the second problem. A mild steel bar has a diameter of 10 millimeters and is 350 millimeters long. A tensile load of 15 kilonewtons is applied longitudinally. Calculate the extension of the bar, if the change in calculate the extension of the bar, the change in diameter and change in volume. Assume Young's modulus for the steel ES is equal to 2 into 10 power 5 newtons per square millimeter, and the Poisson's ratio is 0.25. So this is the given data in the problem. Now to go for the solution, firstly we have to write down the given data. Here the diameter of the bar D is equal to 10 millimeters. So now the next step is we have to find out the area. Cross sectional area is equal to 5 by 4 into D square. So 5 by 4 into 10 whole square. It becomes to 25 into pi square millimeters. The length of the bar is given L is equal to 350 millimeters. Tensile load P is given as 15 kN. So here 15 into 1000 newtons. Here it is the axial force applied along the length. And now the next step is to find out the tensile stress induced in the material. The stress sigma is equal to load by area. So that is nothing but the 15,000 by 25 into pi. It is coming to be 190.98 newtons per square millimeter. Now the next step is we have to find out the increase in length. Here because the body is subjected to the tensile force along the length, so it will increase the length of the bar. So increase in length delta L is equal to FL by sigma into L by E, that is stress into length by Young's modulus. So that is equal to 190.98 into 350 by 2 into 10 power 5. So it is coming to be 0.334 millimeters. So this is the elongation of the bar. Next, we have to find out the longitudinal strain and also lateral strain. So first we will find out the longitudinal strain. Longitudinal strain E is equal to change in length by original length. Here this is the increase in length by original length, delta L by L. So that is equal to 0.334 by 350. So it is coming to be 9.549 into 10 power minus 4. So this is the longitudinal strain produced in the material. Now the next step is lateral strain. Here the given is a round bar or it is a circular bar. So the lateral, because and here also the force is applied along the length. The lateral dimension will be the diameter. So the lateral strain can be found by change in diameter by original diameter. So here, but we know that the lateral strain is equal to delta d by d, and that is also equal to, and also we know that Poisson's ratio 1 by E is equal to lateral strain by linear strain. Therefore, lateral strain is equal to Poisson's ratio into linear strain. So lateral strain is equal to 1 by m into E. That is nothing but the delta d by d. Therefore, delta d is equal to 1 by m into E into d. So substituting those values, so it is equal to 1 by m is 0.25 and E is 9.549 into 10 power minus 4, D is 10. So delta D is equal to 2.387 into 10 power minus 3 millimeters. So this is the change in diameter of the bar. So this is nothing but the change in diameter of the bar. Next, we know that the volumetric strain is equal to 1 minus 2 by m, 1 minus 2 into 1 by m, that is nothing but 1 minus 2 by m into sigma by E or f by E. So that is nothing but the volumetric strain, that is delta V by V. So here delta V becomes sigma by Es into 1 minus 2 by m into V. So here V is nothing but the volume of the bar. The volume can be obtained by multiplying the cross-sectional area with length. So here the 5 by 4 into 10 whole square into 350 will become the volume, and 190.980 is the stress. 2 into 10 power 5 is the Young's modulus, and here 0.025, I think it is 0.25 is the 1 by m value. So substituting those values in the equation, we will get the change in volume is equal to 13.118 cubic meters. So these are the answers. Now the change in length, the change in diameter, and the change in volume of the given bar. Next, we got the other problem. A cylindrical bar is 200 mm in diameter and 1 meter long. During a tensile test, it was found that the longitudinal strain is 4 times the lateral strain. Calculate the modulus of rigidity and Buck modulus. If its elastic modulus is 1 into 10 power 5 newtons per square millimeter, find the change in volume when the bar is subjected to a hydrostatic pressure of 100 newtons per square millimeter. So this is the problem given. Now coming to the solution, first we note down the given data. The diameter of the bar D is equal to 20 millimeters. The length L is equal to 1 meter, nothing but the 1000 millimeters. And the longitudinal strain is given as 4 times that of the lateral strain. The given as the lateral, yes, the longitudinal strain is equal nothing but the 4 times that of the lateral strain. So the lateral strain by longitudinal strain will become the 1 by 4, that is equal to 0.25, and the elastic modulus nothing but the modulus of elasticity or Young's modulus is given as 1 into 10 power 5 newtons per square millimeter. Now we know that the modulus of rigidity can be found. So we know the equation E is equal to 2C into 1 plus 1 by m. So substituting those values, we have E and 1 by M. So 1 into 10 power 5 is equal to 2C into 1 plus 0.25. So 2C into 1.25 is equal to 10 power 5. So whereas C is equal to 10 power 5 by 2 into 1.25. So the modulus of the C becomes 0.4 into 10 power 5 newtons per square millimeter. And next one, the Buck modulus. We also know that E is equal to 3K into 1 minus 2 by 1 minus 2 by M. Substituting the E value and 1 by M value in the equation, the K becomes 10 power 5 by 3 into 1 minus 2 into 0.25. So this week the whole thing will become 0.5. So the K becomes 10 power 5 by 3 into 0.5 and K becomes 0.67 into 10 power 5 newtons per square millimeter. And the to find out the change in volume, we have to find out the volumetric strain. So we also know that the volumetric strain is equal to the K into direct stress. So that can be obtained from the Buck modulus formula. Buck modulus is equal to direct stress by volumetric strain. Therefore, the volumetric strain EV is equal to Buck modulus into Buck modulus. Sorry, the volumetric strain EV is equal to direct stress by Buck modulus. So here the direct stress is given as 100. So in this problem, they mentioned that the bar is subjected to a hydrostatic pressure. So this is nothing but the pressure acting along the length of the bar. So therefore, here the direct stress is equal to 100 and EV becomes 100 by 0.67 into 10 power 5 and that is nothing but EV is nothing but the volumetric strain, that is dV by V. Therefore, dV is equal to 100 by 0.67 into 10 power 5 into V, whereas V is nothing but the initial volume of the bar, that is nothing but the area into length. So here the area is equal to 5/4 into 10 whole square, that is 10 diameter, and length is equal to 1000 millimeters. So that is the volume. So the change in volume will become the 469 cubic millimeters. So this is the change in volume of the given bar under the given conditions. Now coming to the summary part, in this lesson we have discussed about the elastic constants like Young's modulus, E, rigidity modulus C, and Buck modulus K, and Poisson's ratio on M. And also we have noted down the relation between the EC and K. And we also know that the Poisson's ratio on M is equal to lateral strain by linear strain. And we also know the relation between the constants. And we have solved some of the problems by using the relation between the elastic constants, and we could able to found the elastic constants values based on the given date of the problem. Next, so like this we can solve some of the exercise problems, and for this this is the one of the exercise problem and this is the other exercise problem. Like this we can solve these exercise problems to have the clear idea about the finding the different elastic constants using the equations between the elastic constants and the Poisson's ratio. Now here this the relation between the elastic constants is very important. E is equal to, just once again I am repeating the relation between the E and C. E is equal to 2C into 1 plus 1 by m, and the next one is the E is equal to 3K into 1 minus 2 by m. Here this is nothing but the 2 into 1 by m, that is nothing but the 2 by m, whereas 1 by m is the Poisson ratio. And the next relation we got is E is equal to 9 kc by 3k plus c. So these are the very important relations, and with these equations, with these relations between the elastic constants, we can find out any unknown value. Sometimes they may give the E value and 1 by m value, then we are supposed to find out the C value and K value. Sometimes they may give the direct stress, that is K value and 1 by m value, then we may be asked to find out the Young's modulus value. And sometimes the buck modulus and the shear modulus are given, and we are supposed to find out the modulus of velocity. And accordingly, so if you know the relation between the three elastic constants along with the Poisson's ratio, then we can able to find out the any unknown elastic constants, and also we can find out the change in the linear dimension or the change in lateral dimension like diameter or the width or the thickness, and also the change in the volume of the body by using the above equations. So this is about the today's lesson. So thank you all.